On the morning of a quiet lab day in 1999, at a nondescript building on the Harvard University campus, a Danish physicist named Lene Hau did something that, on paper, should not have been possible. She took a beam of light, the fastest thing in the known universe, the cosmic speed limit that Einstein built an entire theory of reality around, and she made it crawl. Not slightly slower, not a measurable delay. She took light that normally travels at 186,282 miles per second and throttled it down to 38 miles per hour. Slower than most cars on a highway. Slower than a bicycle at full sprint. For a few controlled seconds, in a chamber cooled to a temperature colder than the empty vacuum of deep space, light stopped behaving like light at all, and started behaving like something you could almost watch move. If this is the first time you're hearing this, your instinct is probably to assume there's a trick, a rounding error, a misquote, because we've all absorbed the same rule since grade school. Nothing can go faster than the speed of light, and, by extension, the speed of light itself is supposed to be the one constant in the universe that never bends, never wavers, never breaks. It's practically sacred. It's stitched into the fabric of every physics textbook, every science documentary, every meme about spaceships and warp drives. So when someone tells you a scientist slowed it down to walking pace, and later stopped it completely, the reasonable reaction is skepticism. That skepticism is exactly where this investigation begins. Because the claim is real, it happened, it was published, peer-reviewed, replicated, and it sits in one of the most respected scientific journals on Earth, Nature, volume 397, page 594. And once you understand how it was done, and more importantly, what it actually means about the universe you live in, you'll realize the popular version of the speed of light that you were taught was never the whole story. This is the case file on the day physicists broke the speed of light, and the reality behind it is stranger and more important than the myth. Let's establish the baseline first, because on this channel we don't ask you to take a leap of faith. We build the case, brick by brick, from verifiable ground. The speed of light in a vacuum, empty space, no air, no matter, nothing to interact with, is 299,792,458 meters per second. This number isn't just fast. It is, according to Einstein's theory of special relativity published in 1905, the ultimate speed limit of the universe. Nothing with mass can reach it. Nothing carrying information can exceed it. It's the c in E equals mc squared. It defines the structure of causality itself. The reason effect always follows cause. The reason you can't send a signal into your own past. This is not some arbitrary rule pulled from a hat. It emerges from the deep geometry of spacetime, confirmed in particle accelerators, verified by GPS satellites correcting for relativistic time dilation every single day, and tested more rigorously than almost any other number in physics. Consider for a moment just how much of modern life quietly depends on that number being exactly right. GPS satellites orbiting the Earth carry atomic clocks that must be corrected for relativistic effects, predicted directly by the constancy of light speed, and the equations built on top of it. Without those corrections, the location on your phone would drift by miles within a single day. Particle accelerators like the Large Hadron Collider are engineered around the assumption that no particle, no matter how much energy is pumped into it, will ever cross that finish line. Every test ever run, across more than a century of experiments, has confirmed the same result. Nothing outpaces light in a vacuum. That's not a claim any serious physicist, including Lene Hau herself, was ever attempting to overturn. So how do you reconcile that ironclad rule with a lab in Cambridge, Massachusetts, slowing light down to a walking pace? The answer starts with a detail most people gloss over. The speed of light, that's fixed, unbreakable, and sacred, is the speed of light in a vacuum. The moment light enters any medium, water, glass, air, diamond, it slows down. This isn't controversial. This isn't fringe. Every optics textbook on Earth teaches this. It's the entire reason a straw looks bent when you put it in a glass of water, and the entire reason a prism splits white light into a rainbow. Light travels at about 225,000 kilometers per second in water, about 25% slower than in a vacuum. In diamond, it slows to roughly 124,000 kilometers per second, less than half its vacuum speed. This is called the refractive index of a material, and it's one of the oldest, most well-established measurements in physics, going back centuries to scientists like Willebrord Snelius and Christian Huygens. So right there, the myth already has its first crack. The speed of light is not one universal velocity that light always travels at everywhere. It's a maximum, a hard ceiling that only applies in the total absence of matter. The moment light has to interact with atoms, it slows down, because it's not really traveling in a straight, uninterrupted line anymore. It's being absorbed and re-emitted, or more precisely, interacting with the electromagnetic fields of the atoms in its path, over and over, billions of times per second, creating a kind of stutter step that averages out to a slower net speed. Diamond slows light down, water slows light down, even air slows light down, just barely, by about 0.03%. But here's where the story stops being high school physics footnote and becomes something genuinely investigative. If ordinary materials can slow light down by a few percent, or even by half in the case of diamond, the obvious next question, the one a curious skeptical mind should be asking right now, is this: what's the limit? Is there a material, a state of matter, an environment engineered precisely enough that could slow light down not by half, not by 90%, but almost entirely? Could you, in theory, slow light down so much that it becomes observable, a phenomenon you could track, measure, almost watch travel across a room? That question sat, mostly unexplored, for decades. Slowing light dramatically wasn't just a matter of finding a denser material. Glass and diamond are about as dense and optically thick as you can reasonably get before other physical effects take over. To slow light by orders of magnitude, you'd need something radically different, not a passive material light bounces through, but an active, engineered quantum system that manipulates how light and matter talk to each other at the most fundamental level. This is where Lene Hau enters the case file, and where the investigation shifts from established textbook physics into a genuine frontier. Hau, a physicist originally from Denmark and later a professor at Harvard, spent years working with an exotic and extraordinarily fragile state of matter called a Bose-Einstein condensate. To understand why this matters, you need to understand just how strange this state of matter is. Predicted by Albert Einstein and the Indian physicist Sachendra Nath Bose in the 1920s, a Bose-Einstein condensate, often abbreviated BEC, forms when you take a cloud of atoms and cool them down to temperatures within a few billionths of a degree above absolute zero. Absolute zero is the theoretical coldest possible temperature in the universe, the point at which atomic motion essentially stops. Getting within billionths of a degree of that is not something you achieve by accident. It requires lasers used not to heat things, but to cool them. A Nobel Prize-winning technique where photons are used to slow atomic motion down until the atoms practically freeze in place. When atoms are cooled this dramatically, something bizarre happens. They stop behaving like a collection of separate individual particles bouncing around independently. Instead, they collapse into a single unified quantum state, behaving for all practical purposes like one giant superatom that shares the same quantum wave function. It's one of the clearest large-scale demonstrations of quantum mechanics operating in a form you can actually study in a lab, not just in equations. Bose-Einstein condensates were first created experimentally in 1995 by physicists Eric Cornell and Carl Wieman, work that earned them the Nobel Prize in Physics in 2001, shared with Wolfgang Ketterle. For 70 years, this state of matter existed only on paper, a theoretical prediction sitting quietly in the equations of quantum statistics, waiting for technology to catch up with the math. It took decades of advances in laser cooling and magnetic trapping, techniques that themselves earned separate Nobel recognition, before any laboratory on Earth could actually reach the temperatures required to observe one. When Cornell and Wieman finally produced a condensate using rubidium atoms in 1995, it wasn't just a new record on a thermometer. It was the first direct, visible confirmation of a prediction Einstein had made using pure mathematics, 70 years before anyone had the tools to check it. That gap between a correct theoretical prediction and the technology needed to verify it is itself a recurring pattern in the history of physics. And it's the same gap Lene Hau's team would soon exploit to push even further into uncharted territory. Lene Hau realized that a Bose-Einstein condensate, this eerily still, quantum-coherent cloud of ultracold atoms, could be turned into the perfect environment to manipulate light in ways no ordinary material ever could. But cooling atoms to near absolute zero wasn't by itself the trick. The real engineering breakthrough was something called electromagnetically induced transparency, or EIT. Here's the case file version of how EIT works, because this is the mechanism that actually makes the whole experiment possible, and it's worth understanding properly rather than taking on faith. Normally, if you shine a resonant laser beam into a cloud of atoms, the atoms absorb the light almost immediately. The cloud is opaque to that particular frequency, the same way a black wall is opaque to visible light. But if you first hit those same atoms with a second separate control laser, tuned to a very specific frequency, something remarkable happens at the quantum level. The control laser sets up what physicists call a quantum interference effect between two possible energy pathways within the atoms. This interference effectively cancels out the atom's ability to absorb the original beam of light. The cloud, which should be opaque, suddenly becomes transparent to that light, hence the name electromagnetically induced transparency. But this transparency comes at an enormous cost to the light passing through. Its group velocity, essentially the speed at which the pulse of light energy travels through the medium, collapses. Because the light is now forced to interact extremely intensely with the quantum state of every atom in the condensate as it passes through, spending an outsized amount of time exchanging energy with the medium at each point, its effective speed through the cloud drops enormously. This is the physical mechanism, published and confirmed, behind slowing light far beyond what any ordinary transparent material could achieve. Think of it like a massive crowd passing a single rumor from person to person across a stadium. If everyone in that crowd is distracted, confused, or actively resistant, the rumor barely moves. It might not get passed along at all, the equivalent of the light being absorbed and never making it through. But if you first prime every single person in that crowd with a very specific, carefully timed cue, the control laser, the rumor suddenly moves through the entire stadium in a specific, drawn-out, orderly rhythm, person by person, instead of instantly and chaotically. The rumor still gets through eventually. The stadium is transparent to it, but the process of getting through takes far longer, because it now depends on the coordinated, cued behavior of every single person the rumor passes through. That, in an imperfect but useful analogy, is what electromagnetically induced transparency does to a photon moving through a Bose-Einstein condensate. The light gets through, unattenuated, but the group velocity of the pulse collapses because of how intensely and precisely it must now interact with every atom in its path. In 1999, Howe's team at Harvard, working alongside colleagues at the Rowland Institute for Science, published their results in Nature. Using a sodium atom Bose-Einstein condensate cooled to about 450 nanokelvin, a temperature so cold it defies casual comprehension, hundreds of times colder than the coldest measured temperature in outer space, they fired a laser pulse through the condensate under EIT conditions and measured its group velocity at just 17 meters per second. 17 meters per second is roughly 38 miles per hour. For context, that's slower than a competitive sprinter's average speed over 100 meters. Slower than most urban traffic, and almost 18 million times slower than light's ordinary vacuum speed. This was the headline moment. Light, slowed to a speed a human being could plausibly outrun on a bicycle, measured, verified, published in one of the most rigorously peer-reviewed journals in the scientific world. The reversal here, the moment where the unbreakable rule gets complicated, isn't that Einstein was wrong. It's that the rule people think they know isn't the rule that actually exists in physics. The constant, unbreakable speed limit is specifically the speed of light in a vacuum. What Howe's team manipulated was the group velocity of a light pulse traveling through an engineered medium, a completely different physical quantity, no more in violation of special relativity than light slowing down in a glass of water is. Just orders of magnitude more extreme, and orders of magnitude more useful for probing the deepest quantum behavior of light itself. And Howe didn't stop there. If a specially engineered condensate could slow a light pulse down to walking pace, the next investigative question writes itself. Could you slow it down to zero? Could you actually stop light completely? In 2001, 2 years after the initial breakthrough, Howe's team pushed the experiment further, publishing results describing how they brought a pulse of light to a complete, controlled standstill inside a Bose-Einstein condensate. The technique involved sending a light pulse into the condensate under EIT conditions, and then, at a precisely chosen moment, switching off the control laser that was enabling the transparency effect. When the control laser switches off, the medium reverts to its opaque, absorptive state, and the light pulse itself is essentially locked into the condensate. But because of the underlying quantum mechanics of how EIT works, the pulse's information, the actual pattern and structure of the light, doesn't just vanish. Instead, it gets imprinted onto the collective quantum state of the atoms themselves, stored as a kind of matter-based echo of the original light pulse. Then, and this is the part that turns stopped light from a curiosity into something with staggering technological implications. When the researchers switched the control laser back on, the light pulse re-emerged from the condensate, reconstructed, continuing on its way as if it had simply paused mid-flight rather than being destroyed. Light had been converted into a stored quantum state in matter, held there, and then converted back into light on command. This is not a philosophical trick or a semantic reinterpretation of stopped. It was measured, it was reproducible, and it demonstrated something genuinely profound about the relationship between light and matter at the quantum level. That information carried by light isn't fundamentally tied to the photon racing through space. Under the right conditions, it can be transferred, held, and retrieved from an entirely different physical substrate. This is the point in the investigation where the human cost, or more precisely the human stakes of this discovery, come into focus. Because slowing and stopping light isn't a party trick. It sits at the foundation of some of the most consequential technology currently being built in laboratories around the world. Quantum computing is right now one of the most heavily funded and fiercely competitive fields in applied physics, with governments and corporations, from IBM to Google to national research agencies in the United States, China, and the European Union, investing billions of dollars into building machines that use quantum states rather than classical bits to perform calculations. One of the largest bottlenecks in that entire field is what's called quantum memory, the ability to reliably store fragile quantum information encoded in photons, because photons are excellent at carrying information over distance without decohering, and then retrieve that information intact, on demand, without destroying the delicate quantum state. How stoplight work provided one of the earliest, most concrete experimental demonstrations that this kind of storage and retrieval was physically achievable. Photonic quantum memory, dark-state polaritons, the technical term for the merged light-matter quantum excitations that form during the EIT storage process, and slow light-based quantum repeaters for secure long-distance quantum communication, all trace a direct intellectual line back to these experiments. If you've heard predictions about unhackable quantum internet, or quantum computers capable of solving problems classical computers never could, the physical groundwork enabling those systems to actually transmit and store information reliably owes a genuine debt to the ability to manipulate the speed and state of light with this level of precision. The stakes here aren't abstract. Modern encryption, the kind protecting bank transfers, medical records, and classified government communications, relies on mathematical problems that are extraordinarily hard for classical computers to solve, but could, in principle, be cracked far faster by a sufficiently powerful quantum computer. That same quantum future also promises the opposite protection. Quantum key distribution, a method of secure communication where any attempt to intercept a message physically alters the quantum state being transmitted, making eavesdropping detectable in a way no classical encryption can guarantee. Both of these possibilities, the threat and the safeguard, depend on the same underlying capability: reliably storing and retrieving quantum information carried by light across distance without losing the fragile quantum properties that make it useful in the first place. Every satellite-based quantum communication test, every early quantum repeater prototype built in a research lab today is standing on groundwork laid by experiments that first proved photons could be slowed, captured, and released without collapsing the information they carried. There's also a deeper, quieter significance to all of this. One that's less about future gadgets and more about how thin the line really is between impossible and not yet understood. For most of scientific history, the speed of light was treated colloquially as an absolute. Full stop, no asterisks, no fine print. And in a narrow, technically correct sense, within a vacuum, it still is. Special relativity has not been overturned, causality has not been violated. No information was transmitted faster than light in any of these experiments. In fact, quite the opposite. The entire achievement was about making it dramatically slower, and in doing so, revealing details about the interaction between light and matter that were completely invisible at ordinary speeds. But the popular simplified version of the speed of light, the one repeated in casual conversation, in movies, in offhand comments about the impossibility of certain physics, turns out to have been an oversimplification the entire time. The rule was never, light always moves at this one speed. The rule was, and remains, nothing exceeds this one speed in a vacuum. Those are two very different statements, and conflating them is exactly the kind of myth this channel exists to dismantle. This is also a useful moment to be honest about what didn't happen, because part of being evidence first means being just as clear about the boundaries of a discovery as its substance. Nothing about House experiments broke special relativity. No particle exceeded the vacuum speed of light. No information traveled backward in time or violated causality. These experiments didn't disprove Einstein. If anything, they operated entirely within the framework Einstein and later quantum physicists built, using well-understood atomic physics, quantum interference, and precisely controlled laser systems. What they broke was a piece of pop science shorthand, the idea that the speed of light is some single, unchangeable velocity that light simply always moves at, everywhere, under all conditions. That version of the rule was never accurate. It was a simplification that worked well enough for everyday intuition, but fell apart the moment scientists built an environment precise enough to test its actual boundaries. It's also worth putting the sheer scale of this experimental achievement in perspective, because it's easy for a number like 450 nanokelvin to slide past without registering just how extreme it is. The average temperature of the vacuum of outer space, warmed slightly by the residual glow of the Big Bang, is about 2.7 Kelvin. House condensate was cooled to a small fraction of a single degree above absolute zero, colder than anywhere else known to exist in the observable universe at that time, colder than the depths of interstellar space, achieved not in some remote facility, but in a university laboratory using lasers, magnetic traps, and evaporative cooling techniques refined over years of painstaking experimental work. That's the price of admission for the kind of quantum-scale precision required to manipulate light this dramatically. And it underscores that this wasn't an accident or a fluke measurement. It was the product of exact, deliberate, repeatable engineering at the outer edge of what temperature control and quantum optics could achieve at the turn of the millennium. So where does that leave the original claim, the speed of light isn't the real limit, scientists already broke it? The honest case file answer is this. The constant, the true unbreakable limit, is very much still intact. Nothing in this story threatens the speed of light in a vacuum as the ultimate cosmic speed limit. What was broken was the misconception that this limit applies uniformly to every situation involving light, everywhere, at every moment. The myth that the speed of light is a single fixed velocity, rather than a maximum ceiling that light only reaches in the complete absence of matter. In every material, in every medium, in every engineered quantum system, light's actual measured speed is negotiable. And Lene Hau's team pushed that negotiation further than anyone before them. First to a walking pace, then to a dead stop, and then back again. That distinction matters far beyond a semantic technicality, because it changes how you should think about unbreakable rules in science more broadly. Very often, when a scientific claim gets broken in dramatic fashion, the underlying fundamental law hasn't actually failed. What's failed is the layperson's understanding of exactly what that law claims to cover. Special relativity speed limit was never about light always moving at one speed. It was about nothing exceeding light's vacuum speed. Hau's experiments are a masterclass in exploiting the space between those two ideas, using deep, rigorous, verifiable physics to manipulate something everyone assumed was untouchable, without actually touching the one thing that was truly sacred. If there's a bridge to today in this story, it's not just about quantum computers on some distant horizon. Research building on this foundational slow light and stock light work continues actively in labs around the world, extending into fields like quantum networking, precision sensing, and even attempts to use similarly engineered systems to study analogues of black hole physics, where dramatically slowed light can be used to model event horizon-like conditions in a controlled lab setting rather than an inaccessible region of space thousands of light years away. In these analog gravity experiments, physicists create a flow of ultracold atoms moving faster than the local, drastically reduced speed of light within that medium, mimicking in miniature the point of no return at the edge of a black hole, where not even light can escape. It's a way of testing predictions about extreme gravitational physics, including aspects of Hawking radiation, without needing an actual black hole nearby. And it exists only because researchers first learned how to slow light down enough to make such a comparison physically meaningful in the first place. The techniques pioneered in these experiments have become tools scientists use to probe some of the strangest corners of physics, precisely because they demonstrated that light, this thing we treat as instantaneous, untouchable, and universally constant, is, under the right conditions, remarkably responsive to careful engineering. Lene Hau herself continued this line of research for years afterward, extending the work into areas like using stop-light techniques to generate and study exotic quantum shock waves within condensates, and exploring how matter-based storage of light could eventually contribute to hybrid quantum systems that combine the best properties of photons, fast, low-loss transmission, with the best properties of matter, stable, long-term storage. None of this rewrites Einstein. All of it depends on him being right. There's one more piece of this case worth putting on the record, because it's the kind of detail a truly skeptical viewer should be asking for. Has anyone else replicated this? Science doesn't consider a single result, however dramatic, to be settled fact until independent groups confirm it. In the years following Howe's initial 1999 and 2001 papers, other research teams, including groups working with different atomic species and different experimental setups entirely, some using warm atomic vapor cells rather than ultracold condensates, successfully demonstrated slow light and stop light effects using the same underlying electromagnetically induced transparency mechanism. The core physics held up. The effect wasn't a one-off anomaly tied to one lab-specific equipment. It was a genuine, reproducible property of how light interacts with precisely prepared quantum systems, confirmed by multiple independent groups using variations on the same fundamental technique. That's what separates a verified scientific case file from a viral claim that collapses under scrutiny, replication, publication, and survival under independent testing. So the final verdict on this case is layered, and that's exactly how good evidence should leave you. The headline claim, that scientists broke the unbreakable speed of light, is true in the sense that matters for a documentary hook. Light was slowed to a walking pace, then stopped entirely, in direct contradiction of the popular, oversimplified version of the speed of light that most people carry around without ever questioning it. But the deeper, more precise claim, the one that actually holds up under the scrutiny this channel insists on, is that Einstein's true speed limit, the constancy of light in a vacuum, was never touched, never threatened, and remains as solid today as it was in 1905. What broke was a piece of folk physics, a shorthand that had outgrown its accuracy. What survived, and was in fact reinforced by every measurement in this story, is the actual law of physics underneath it. So the next time someone repeats the line that nothing can be faster or slower than the speed of light, you now have the case file to set the record straight, not by disputing Einstein, but by adding the detail that got lost in translation somewhere between the physics classroom and popular memory. The speed of light is the ultimate limit in a vacuum, uncontested and verified to extraordinary precision. But light itself, moving through the matter of our universe, is far more negotiable than the myth ever allowed, slowed to a crawl, stopped entirely, and released again, in a laboratory, by a physicist who looked at an unbreakable rule and found the fine print everyone else had missed. If this kind of evidence-first reframing of a settled scientific fact is exactly the kind of investigation you come here for, you already know what to do. Stay subscribed, because the next case file is already being built, and the next myth is already waiting to be checked against the evidence.